All right, hi guys. We are actually moving back to a chapter we've kind of already done before. You guys are so fast. We're kind of through everything that we need to get through. So what we're going to talk about today, we're going to kind of do some fun stuff. We're going to look at solving systems of equations in three variables. And really why I want to do this is because what I want to get to is showing you how to solve these systems using a matrix. So you've probably used or maybe worked with matrices before. But what we're going to do in this section is we're going to do it by hand. And then that gives us an appreciation for how to solve these using our calculators in the next section. So solving systems of equation in three variables. We've done two variables before, but a system of equation in three variables, is something like this. So like 4x plus 2y plus 5z equals 6. See how that z came in? So that's where we're going to get our system of equation in three variables. So I'm just going to put an example here. And then we'll talk about like how we're going to do this and the rules and the things that we're allowed to do with these systems. So for example, something like this is a linear system. It's a linear equation in three variables. Well, linear system. And why do we say it's linear? Because every term in the equation has an exponent of 1. Okay, so that's what we mean by it's linear. And then when we solve this equation, a solution is an ordered, so a solution to this equation is what we call an ordered triple. So if you notice, I have three unknowns, right? So my ordered triple is going to be an x, a y, and a z. Okay, and that x, y, and z, that is going to be an x. Those are going to be numbers that satisfy all three equations simultaneously at the same time. If you have ever done anything with 3 dimensions, like 3D graphing, so when we have like, depends on how people do this sometimes, but this would be maybe my z, this is my x, and this is my y, or vice versa. Sometimes this can be y and that can be x. What we're actually looking at here is these equations here describe a plane in 3 dimensions, and so we're looking at the point where maybe 3 planes intersect. Okay, a couple things we can do with systems of 3 equations. Things we can do without changing the solution. We can interchange any 2 equations. Okay, so I can write the first one as the second one as the first, stuff like that. That does not change the solutions to the solution or solutions to the system. The other thing we can do is we can multiply both sides of one equation. So these are the things we can do without changing the solution. So both sides of one equation, I'm going to get a little lazy here, which shouldn't surprise you, by a non-zero constant, which we know we can do with regular old equations. So that should, I can multiply both sides by something, and I don't actually change the solution, which we would hope would be true because we have an equality. And then the other thing we can do is we can add a non-zero, go away, come on. I can add a non-zero multiple of one equation to the other. Multiple of one equation. And this is going to be the key, really. Whoa. To another equation. So those are the things we can do, you guys. We can interchange any 2 equations. We can multiply both sides of one equation by a non-zero constant, and I could add a non-zero multiple of one equation to another. And we're going to see basically what our goal is going to be is to get rid of one variable in 2 equations and then break it down to a system of 2 equations, which we know how to solve using substitution or elimination. Okay, I'm just going to grab these examples from your book because apparently I am feeling quite lazy today. So let's solve the following equation. All right, so we have x minus 2y plus 3z equals 11. I'm going to call this equation 1. And then I have 4x plus 2y minus 3z, oh, they're being nice to us, equals 4. This is equation 2. And then I have 3x plus 3y minus z equals 4. So the reason I said they're being nice to us is because let's look at equations 1 and 2, right? If I look at equations, so I'm going to do this probably a little differently than the way your book is going to do, but if I look at equations 1 and 2, do you see how I can actually, if I add 1 and 2 together, and that's 3, I'm actually going to be able to solve for x right away. So that's what I'm going to do. And I'd like you to tell me what you're doing. So I'm going to take equation 1 plus equation 2, okay? So if I add equation 1 and equation 2, I'm just going to add straight down. I get 5x, so this is a pretty easy one. Notice if I add, my 2y's are gone, and if I add here, my 3z's are gone, and then 11 plus 4 is 15. So usually that doesn't happen. They just give you kind of a nice one for you to work out. But right away now, what do I see? I see that x is equal to 3. Okay, so now I can go back and I can choose 2 of these equations. I know that x is equal to 3, and I'm going to be able to solve for one of the other variables. Now, I'm not necessarily going to want to work with 1 and 2, because if I add these 2 together, I'm going to get a 0. I'm going to end up getting 0 equals 0, which isn't going to help me too much. So what I'm going to actually do is I'm going to take that 3 here, and I'm going to plug it into equation 2 and equation 3. Okay, so plug x equals 3 into 2 and 3, and then I'm going to get a system of 2 equations, which I know I can solve using, whoa, that was a crazy line, substitution or elimination. Okay, so if I plug in that 3 in there, I get 12 plus 2y minus 3z equals 4, and then I get 15 plus 3y minus z equals 4. So what does that imply? That I have 2y minus 3z equals negative 8. Just subtract that 12 over. And then I have 3y minus z equals what? Negative 11. Okay, now I'm ready to go. So I am going to take this equation here. I'm going to do elimination, and I'm going to multiply it by a negative 3. I'm going to multiply by that negative 3 so that these guys are going to cancel out. So look at what I get down here now. So I still have the 2y minus 3z equals negative 8. And if I multiply this by negative 3, I get negative 9y plus 3z. That was the whole reason I did it. Don't forget to multiply this negative 11 by negative 3. That gives me a positive 33. Now I'm going to add them. My 3z's cancel. And I get a negative 7y, right, equals, what do I have here? 25? I think I made a mistake, because I think I should get a nice solution. This is what happens when I have to do these on my own without anyone making sure I'm doing them correctly. Okay, I think you guys saw, I bet you were yelling at the screen back here. Sorry about that. I had to stop the video and make sure I did this correctly, which I did not. That's a 9. So this right here, this is going to be so much better. That's going to be much, 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 much better. I was kind of wondering what was going on here. So that's a negative 5. Oh, that's much better. That's 15. That's 7. And now what do we get? Then we get y equal to negative 1. Beautiful. So now let's see, what we have. So I have that x is equal to 3. I have that y is equal to negative 1. And now I need to find z. So I'm going to take, I don't know how that worked. I'm going to take that y equals negative 1, and I'm just going to pick one of these 2 equations here to plug that negative 1 into. So let's just take the top equation. It doesn't really matter. So I'm going to have 2 times negative 1 minus 3z equals negative 8. That gives us a negative 2 minus 3z equals negative 8. So I add the negative 2 over. That gives me a negative 6. And then negative 3 divided by negative 6 is a positive 2. So just like we stated our solutions with systems of 2 variables as an ordered pair, now I want you to state your solution as an ordered triple. So my solution then is going to be 3, negative 1, and 2. And what does that mean, right? Again, what that means is if I plug those numbers into that first, second, and third equation, then I'm going to get a true statement. Then that's going to work. And so that's my solution. That's where the three planes meet up, that point. And if you do look at how you graph that, if you guys have done this at all, if that's my z, that's my x, that's my y, that x tells me to come over 3 in the x direction, then 2 in the y direction, and then z is usually the up and down. So I would go down through the xy plane, and I would go down, or excuse me, come up, that's positive 2, through the xy plane and go up 2, and I'd have this point up here. Okay, and sometimes you can like draw little arrows. I don't know if you can kind of see that, but oh, I should move that point over. But that's what that solution means, and that's where those three planes intersect. It's pretty cool. Let's just do one more example of this, and then what I want to do is I want to do a couple of applications and then call it good. So let's solve one more example of this. So let's look at x plus y plus z equals 7. Actually, yeah, this one will be fine. 3x minus 2y. I know I'm not gonna do a lot of these examples, but I think once you get going on these, you'll see they're kind of labor intensive. They kind of take a while to do, but the actual process of it isn't too bad. So let's look at one like this. So I have equation 1, equation 2, and equation 3. Okay, so what I want to do is I want to get rid of one of the variables. That's going to be my goal. And if you notice in this one, unlike the last one, I can't just add 2 equations and get rid of that variable. So there are some options here. We can multiply this second equation by 3 and add them together. Or I could get rid of the z's right here pretty well and add it together. So I think maybe what I'll do is I'm going to multiply equation 1. Oh, let's look at the x's, actually. I'm going to try and kind of follow what your book does here. Let's look at the x's. So lots and lots of options, you guys, on how you can do this. You guys will all probably do this a little bit differently. But what I'm going to do is I'm going to take -3 times equation 1, and then I'm going to add that to equation 2, okay? So I'm going to take -3 times equation 1. That gives me -3x minus 3y minus 3z equals -21. Don't forget to multiply that last term. I forget sometimes. Ask me how I know. And then I'm just going to leave equation 2, and I'm going to add these together. Remember, these are one of the things that I can do with these systems of 3 equations. So look what happens when I add them. My x's are gone. I'm left with -5y minus, minus 2z, right, equals a -18. So this one, again, isn't quite as simple as the last one. So I'm going to kind of hold on to that one in the back of your mind. I have this equation here. And now what I want to do is I want to go and I want to use 2 of the other equations so that I can get another equation with just a y and a z. And so to do that, I'm going to add, let's see. Well, I'm gonna, sorry, I'm gonna take, let's go ahead and just take equation 1. So I'm gonna take equation 1 and I'm gonna add it to, -1 times equation 3. Do you see how that's going to give me, doing this a little bit differently than your book now, that's going to get rid of the x's again. Now, I don't want to use the same 2 equations I used before. I used equation 1 and equation 2. Don't use those again. You're just going to get the same thing back out. But now what I'm going to use is I'm going to use equation 1 and equation 3 to, again, get a system of just y's and z's. So if I do that, so I have x plus y plus z equals 7. And then if I take a -1 times the third one, I get a -x minus 6y, okay, minus 3z equals -25. And let's add those together. So look at what I'm going to get. I'm going to get a -5y, right, minus 2z. And then what do I get here? Equals, that's a -25. You can't really see that, -18. So I'm going to now use these two new equations. So sometimes we'll label these. We'll say like this is equation 4 and this is equation 5. And I'm going to solve these two equations. And I'm sure you can kind of see what's going to happen. But how am I going to solve these two? Well, I can see I can get rid of the y's right away. So I'm going to add 4 and 5 together. Okay, if I add 4 and 5, what you're going to see is this is going to be a dependent solution. If you remember those dependent solutions back when we talked about equations of two variables, because look at what happens. I get 0 equals 0. So the only thing that really matters here is that we have some, well, if you ever take linear algebra, we have something called a free variable. But 0 equals 0 is a true statement. I'm not getting a contradiction. So this is not, if you get a contradiction like 5 equals 0, then we know we have an inconsistent system, or we know that there is no solution. But this actually is just telling us that like one of these lines is exactly like the other line. And I think you can probably see that if you look at some of these equations, you'll see that they are kind of the same if you kind of mess with them a little bit. But what we're going to do then is we're going to take this equation. Remember when we did this before? I'm actually going to solve this equation for y. One of these equations. Well, they're the same equation. And I'm going to describe my solution in terms of one of the variables. And so in this case, I'm just going to choose z. And I think your book chooses z, so you can do that also. I'm just going to solve for y. I'll let you do that. That y, if you solve for it, becomes a negative 2/5 z, okay, plus 18/5. Okay, so I get y equals a negative 2/5 z plus 18/5. And now the fun part with this, so that is going to be one thing that describes what y values are going to be. Now what you're going to do is you're going to take that guy and you're going to substitute it in to one of these three equations here. I really recommend substituting this into the first equation, because as you can see, if I substitute this into equation 1, okay, so I'm going to put this into equation 1. And what I'm looking for here is I'm looking for a way to rewrite x now in terms of z, so that I can describe everything in terms of z. Because this is a dependent solution, it's all going to depend on z. I could just have easily picked a different variable to solve for. I could have solved for z and made everything in terms of y. So I substitute this back into equation 1, and what do we find? We find that x is a negative 3/5 z, okay, once you solve it, plus 17/5. I'm being really lazy too, and I'm using your book. So let's see what we have. We know that this is x. You give me a z value and I can find x. You give me a z value and I can find y. So here is how we're going to describe the solution. Okay. Again, this is a dependent system. There are an infinite number of solutions. I'm going to describe the solutions. Well, my x is 3/5 z plus 17/5. I don't have a whole lot of room here. What is my y? It's a negative 2/5 times whatever my z value is going to be, plus 18/5. And then what is z? Well, z is going to be that independent variable. We get to pick z, and then y, right, and x are all dependent on whatever z is. So that's my solution. I know that's a little bit weird, but that's a solution. That's an example of a system that has an infinite number of solutions, but they're dependent on whatever we choose z to be. All right, so now I just want to look at a couple of applications and then we'll call it good. So again, I'm being a little bit lazy here. I am grabbing an application from your book. So pause the video if you want and write this down. I just don't want to write all of this. So look at what we have. We have in a group of 100 adults, 70 people say they're most likely to do spring cleaning in March, April, or May. Of these 70, the number who clean in April is 14 more than the number who clean in March and May. The total number who clean in April and May is 2 more than 3 times the number who clean in March. Find the number who clean in each month. Okay. Blah, 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 right? So what I want to do is I want to make sure that I am defining all my variables. So I'm going to define my variables. What don't I know? I don't know March. How many people clean in March, April, or May? So I'm going to let m equal the number of people who prefer March. Okay. For March, I know this is getting a little crazy. I'm going to let a equal the number of people for April. I know I'm getting wild. Oh, and then they had to do May. Let's use y. which spells May, that's funny, for the number of people in May. Okay, who prefer May. Now, here's what's tricky about this. They say that there's a group of 100 adults. That actually doesn't matter. What matters here is that we're talking about the people that enjoy most likely to do spring cleaning. So my first equation that I know is I know that if I add up the total number of people that prefer March, the total number of people that prefer April, and the total number of people that prefer May, that is going to equal 70. Okay, there are 70 total people that wanted spring clean in those 3 months. So now here's the key. Let's look at what this is saying. Of these 70, the number who clean in April is 14 more than the total number who clean in March and May. So let's take that silly English and turn it into beautiful mathematics. So the number who clean in April, so April, right, is, that's easy, is 14, okay, more than the total number who clean in March and May. Well, the total number who clean in March and May would be March plus May. So do you see there how we have an equation that we can write out in terms of all three variables, right? Just by reading that sentence. That was a good time. I had fun there. The total number who clean in April and May is 2 more than 3 times the number who clean in March. So this is our last equation here. The total number who clean in April and May, so April plus May, I love doing these, I think they're so fun, is 2 more than 3 times the number that clean in March. Okay, I hope that makes sense. So those are our 3 equations, all right? I'm going to go ahead and rewrite these in the order that we're kind of used to seeing them in. And so I'm going to kind of put a little thing here. So I know I have M plus A plus Y equals 70. And you sure could, I'm going to use elimination here, but you sure could do substitution actually in this case. It wouldn't be that hard to do. And notice, why is stuff turning negative? Because I'm just bringing everything over. Plus A plus Y equals 2. That's what I'm going to call my 3 equations. Okay, and again, you could do some substitution here. There's actually kind of a lot of ways that you can solve these, but I'll just stick with kind of the way that we've been talking about. So look at this, is going to be pretty nice. Notice if I add 1 and 2 together, that gets rid of my Y's and my M's. So I'm going to take 1 plus 2. Okay, if I do that, look, my M's are gone, my Y's are gone. I get 2A, right, equals, I'm just adding them straight across, 84. Awesome. So what does that tell me? That tells me that A then is going to be 42. That's great. Okay, A is going to be 42. Now, I don't want to plug that into my original 1 and 2, right? Because then if I try to solve that, I'm just going to well, you probably could try and solve it, but it's just not going to work out super well. So I'm going to take that A equals 42 and I'm going to plug it into 2 and 3. Okay, so A equals 42 into 2 and 3, and let's see what we get. So I get a negative M. If I have that plus 42 right here, I'm going to go ahead and just subtract it over. So I get a negative M minus Y equals 14 minus 42, which I think is 28, negative 28, excuse me. I keep doing that. Let's make sure I get that correct here. Negative 28, my bad. And then if I put in the 42 for this guy, this gives me negative 3M plus Y, right, equals, I can do that one, negative 40. And look at you guys, if I just add these together, right away, look at what I get. I get a negative 4M, my Y's cancel out, equals a negative, what, 68? So what is M going to be? Well, if I divide by a negative 4, it looks like that's going to be 17. And now what do I know, you guys? I know that A plus M plus Y all equals 70. So I can find Y just by taking 70 minus 42 minus 17. And you know what? I'm going to use my calculator. Seems like the higher I get in math, like the worse my arithmetic skills get. So what do I get Y to be? Y equals 11. And of course, I'd put a nice, pretty little bow on it by writing this in a sentence. So the number who prefer cleaning in March is 17. The number who prefer cleaning in April is 42. And the number who prefer cleaning in May is 11. I hope that makes sense. I hope that's pretty straightforward. I think that probably is. Okay, let's look at one more example and then we'll be done. All right, last example. So Casey receives $126 per year in simple interest from 3 investments. So remember, simple interest is just applying the interest rate, and that's it. There is $500 more invested at 3% than 2%, all this stuff, right? So we have so here's the stuff that's important, 2, 3, and 4%. So I'm going to let X equal the amount of money in the 2% account. Okay, I'm going to let Y equal the amount of money in the 3% account. And I'm going to finally let Z equal the amount of money that Casey has put, congratulations, Casey, in the 4% account. Okay, so let's see what this is saying. Casey receives $126 per year in simple interest from 3 investments. So let's talk about how you find the interest. So the interest in this account is going to be 0.02 times X, okay? That's how I find simple interest. I just take 2% of the amount of money. So if I think about the total interest, I'm going to take 0.02X plus the interest made in my Y account, or in my 3% account, excuse me. I could say that. So 3% of Y plus the interest made in my 4% account, which would be just 4% of the how much money I have in the account. This is all going to equal $126. That's how I describe the total interest made in all 3 accounts. And now, of course, they have to give us more information, right? What do we know? Part is invested. Oh yeah, I know that. Sorry. The amount invested. Sarah, come on. I haven't had enough coffee this morning. There is $500 more invested at 3% than 2%. So that's going to be a pretty easy one to do. So there is $500 more invested at 3% than 2%. So what does that say? That says 3% is $500 more. Sometimes I have to reword it than 2%. So what does that tell me? The amount of money in my 3%, so that's Y, is, right, $500 more than the amount of money that's invested in my 2%, which is my X. I hope that makes sense, right? That's how I rewrite that sentence. There's $500 more invested at 3% than 2%, or the money in 3% is $500 more than the money in 2%, okay? So again, 3% is $500 more than 2%. And then the last sentence says the amount invested at 4% is 3 times the amount invested at 3%. So this should be pretty straightforward. The amount invested at 4%, so that's Z, right? The amount invested at 4%, that's Z, is, right, 3 times the amount invested at 3%. So that's 3 times Y. Okay, I hope that makes sense. And this one, actually, I am going to do substitution because this is just asking for you to do substitution with one like this. So what I'm going to do actually here is, so this is 1, this is 2, and this is 3. So look at what I know. I know that Y is in terms of X. If I can get Z in terms of X also, then I can replace this Y and this Z with stuff in terms of X and be ready to go. So look at the Z. If Z is 3 times Y, that means Z is 3 times the 500 plus X. Does that make sense? I hope so. So that's 1500. I'm just doing a straight substitution plus 3x. And now I'm going to take these 2 equations. I'm going to take this guy here and this guy here, and I'm going to substitute it in to my original equation. Once I have x, I can do a back substitution. So I have 0.02x plus 0.03, not times y, but times 500 plus x, plus 0.04 times, what is z in terms of x? 1500 plus 3x, right? That all is going to equal 126. I hope that makes sense. Now you're going to simplify. I'm using my calculator because I don't trust myself. So I end up getting 0.09x. That's just by taking, distributing this guy through to each one. And let's see what we get. 1500 times 4.04. That's 60.03 times 500. So 15 plus 60 plus, oh, that's all we got, I think. So I think this is just plus 75. Okay, equals 126. Yeah, that looks good. So 126 minus 75 is 51, and divide 51 by 0.09. And here it looks like X is $566.67. I can't guarantee I haven't made a mistake there because I really have not had enough coffee this morning. So hopefully that looks right to you. I think it is. Am I missing anything? No, I think we're good there. So what do I do then with that X value? Well, look at you guys. I've already done all the work for myself. Here I know that Y is just 500 plus that. And then I know that Z is 1500 plus 3 times that. So that means that Y then, right, if I add 500 to that is $1,066.67. And then Z, if I take that 566.67 times 3, well, that's $1,700 if I hadn't rounded, and then plus 1,500 is about, but since I did round, let's be consistent with that, $3,200.01. That one was a good time. I really enjoyed doing that one. I hope you did too. That's fun. Again, just take those sentence by sentence. You'll get a system of 3 equations, and then you just kind of solve that system, mess around with it, try stuff out, see if it works, and have fun.